Did you guys do this one? It was on your homework. Right, it's not terrible, is it? Were you able to do it? Okay. Did any, because nobody asked questions until this morning, but you've had it. Well, I shouldn't expect you guys to look at this stuff until the night before it's due, probably, but you've had it in front of you for over a week. So um, I was surprised that I didn't get any questions on it. It made me assume that you guys were pretty good with this. So is that true? Like, this is an acceptable test question, in my opinion. It's very straightforward. If that's not true, you should ask more questions. Why do you think that's out there in front of you? Or are you planning on doing it tonight after school since it's not due till midnight? Or it was due Friday, wasn't it? It was due tonight. Okay. So I guess some of you don't plan to start yet because I'm just looking at some faces and a lot of you don't know what I'm talking about. So this is what you have to look forward to then. Good luck. Go ahead.
The AP classroom that's for the submission on Canvas isn't open. Like submit any PDF or anything.
So you need me to change it to submit the PDF. I will. Well, I won't remember this conversation. Can you send it as a Canvas message?
Yes, sir.
That would help. Because I would love to say I'll run over there between classes and do it, but I'm pretty sure I'm going to be preparing tests between classes.
Sure we will.
Well, if I were you, this is an excellent question. You should pay attention to it tonight, or have done it ahead of due date, maybe a day before. But I get you. It's not due till midnight. No reason to start it until 11:45. So good luck. All right. We ended our day on Friday, I believe, with the electric potential for a single point charge in space, fitting this description for a location, a distance, r away from the charge. This is the electric potential. And with that, we know that the electric potential energy at any location around the charge will depend on what charge you place there. But if I place a charge anywhere in the vicinity of the other charge, it will have an electric potential energy equivalent to this. So this is obviously in joules. But the electric potential is not. It's in joules per coulomb. Again, which we defined as a volt. Okay. Now, I want to just do a quick aside for just a minute, because you've probably heard about this, but you may not know what it is. How many of you have heard of an EV before? Do you know what EV stands for? It stands for an electron volt. That's right. It's a unit of energy, is the electron volt, and is generally used for small amounts of energy at the atomic scale. It should be clear that it's a unit of energy because it's a charge of the electron multiplied by the value of a single volt, an EV. So there's it's clearly the product of charge and voltage. Now the EV is used for small amounts of energy. Like I said, usually related to things like the values given to electrons. But as an energy amount goes, you should realize that it's just another form of energy. So there's a conversion from electron volts to joules. And it shouldn't be too hard. In fact, I think you should be able to work out what that conversion is. And I'm not going to do it right now, but you should think about it. But what I'd like you to tell me is how fast would an electron be traveling should it have fallen through a potential difference of 1 volt? If you don't know what I'm asking, think about the words I just used, because it's not much. I didn't give you much information to go on, but there's not much there either. How fast would an electron be going if it fell through a potential difference of 1 volt? Now, the wording I'm using, I'm not using accidentally. I'm using this wording because it's used like this a lot. So don't think too hard on it. It's not much there, but at least try. I'm going to put some information up here that would be viably necessary to solve this question. The charge on the electron you should already know, but I'll put it here again anyways, 1.6 times 10 to the negative 19th coulombs. You're also going to need the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. And I'd like my answer in meters per second. Again, I don't want to spend that kind of time, too much time on this. We need a region of space that has a potential difference applied to it. So I'm just going to take, say, 2 plates, put a hole in one of them, and apply a potential difference of 1 volt between them, making sure this is the low side and this is the high side, and drop my electron right there. Now the electron can fall across a potential difference of 1 volt. That's all I said, that we're going to accelerate the electron. You understand, if I put a potential difference of 1 volt here, I am creating a plate that's negative and a plate that's positive. Probably done so because I moved charges from one side to the other. That could be one way to do it. And once this potential difference is established, when I drop the electron in there, it will immediately have a potential energy that is equal to Q times V. Well, V's 1, and Q is the charge. But the electron's going to accelerate this direction. It'll be accelerated away from the negative charge in the plate and towards the positive charge of the other plate. Its change in potential energy will have to equal its change in kinetic energy. Since its final potential energy will be 0 and its initial kinetic energy will be E times V, that suggests its final kinetic energy will be 1/2 mv squared, and its initial kinetic energy is 0. All right? Charge in the electron's negative, so this is really it. This was all we were asking. And I gave you M. See, once I know the potential or the potential difference, I know stuff about the energy, but I have to know what charge we're dealing with. I'm not going to plug the numbers in. That's the least you guys can do. But again, it comes out to be about 6 times 10 to the 5th meters per second. Speed of light, 3 times 10 to the 8th meters per second. Is 6 times 10 to the 5th appreciable to the speed of light? Like, do you think we're approaching it yet at that speed? It wouldn't require a relativistic correction. But the backs of televisions usually have accelerating potentials of around 150,000 volts to 300,000 volts. So this is the old style televisions that use a cathode ray tube. Those voltages can accelerate electrons up to relativistic speeds. And since those were used in televisions, if you wanted to get the timing exactly right and sharpen your picture up, you had to make relativistic corrections to the timing as you're trying to display something on the screen. But 1 volt, no, it doesn't require a relativistic correction. All right, relatively straightforward, but I'm going to ask some other relatively straightforward questions as well, okay? And I say, this is just stuff from last week. Ready to go? If the plates are separated by 1 centimeter, what's the electric field between the plates? All right, well, again, some of these things should be faster on the recall, I think. There is an electric field between these 2 plates, right? Does that surprise you? Is anybody surprised by that idea? Except I'm drawing my arrows wrong for the electric field. That's the direction that the electron went. So let me at least draw arrows that make sense for the electric field. They are this way because the electron went the other way. So there we go. So we have an electric field between the plates like that. It's a uniform electric field, and a uniform electric field unless we get towards the edge. So if I use that idea, and we've talked about this before, the potential difference as you move through a region of space that has a uniform electric field is just going to be equal to E times D, which we also talked about the work done in moving a particle through a region of space with a uniform electric field would have been that. Actually, I think we said this is the potential energy if you moved a charge from one place to another in a uniform electric field. So we know that it's 1 volt and they're separated by 1 centimeter. So this was it. That's all I was asking. The electric field between the plates is going to be 100 units here, though. I want you to think about the units. That's why I asked the question. If we look, you can find the electric field by taking the voltage divided by the separation distance, sure. If it's a uniform electric field, and between the plates of two parallel plates like this, it would be uniform. So notice what these units would look like. This would be volts per meter. Not our normal way of writing the electric field's units. If you remember, when we talked about electric field a long time ago, it was force per unit charge, which was newtons per coulomb. Are volts per meter and newtons per coulomb the same? Now, I would love to see you guys do that. I'm not sure you can, but I'd love to see it. Can you try? Can you show if newtons per coulomb is the same as volts per meter? You may need to know what a volt is, which I just told you a moment ago. You guys are just hard to watch. I gotta be honest, just hard to watch. How would you do it? Well, you could do it either way. You could try and make one become the other, or you could just break them both down to their base elements. So that'd be okay too. Not knowing how to do this is one thing. Not knowing or unsure of like the process of showing if they're equal, that was quite another I was not ready to expect. So yeah, you could just break them down to their base elements, like the base units. A newton is a kilogram meter per second squared. That'd be the first one I would start with. So if you want to do it that way, kilogram meter per second squared per coulomb. But you would have to know what a volt was. A volt is we just said it a moment ago. What is it? It's a joule per coulomb. So I replace volt with joule per coulomb. And now I'll replace joule with its next broken down unit, which is what? Newton meter. And I'm already pretty much shown that they're the same, right? But yeah, we can just go one step further if you're desperate for it. That ended up being way harder than it should be for you guys. The plates in the back of a television that do this are actually pretty small. It's usually circular, the two plates, and they have a diameter of about 1 centimeter. So what's the charge on the plate? You've got everything you need to do it. Something else from a couple of weeks ago. Can you figure out the charge on one of the plates knowing that the diameter of the plate is about 1 centimeter? You're supposed to have this one memorized, this equation. Let's see if you do. The electric field near a charged, a sheet of charge is charge density over 2 epsilon naught. supposed to have that memorized. The problem is that you can't use this here because there's two of them, so you have to double it. So multiply it by 2 for the contribution to the electric field, one from each plate. That was on your test last too, by the way, just if you don't remember. All of you ready for today's test, this is useful information. If today's test is the same as last time's test, luckily I had time to rewrite it, so it's not. But that gives me this, right? And we know the electric field is 100 volts per meter. However, I asked for the charge on the plates. This is in terms of charge density. So I'll have to replace sigma with something that's an expression for the charge density, which should be the charge per unit area. So Q over pi r squared. That's it. That's all this is. And yes, I'm expecting you guys to remember things. They're all very, very easily related here. So just a little bit of substitution here, and I get 100 equals Q over pi epsilon naught r squared. R is 0.5, I'm sorry, not 0.5. It's 1 centimeter, so 0.005 meters. Right, the diameter was 1 centimeter. You need the radius, so. Still not asking anything particularly hard yet, am I? This is all pretty straightforward. So, with this thing, right? We dropped our electron through 1 electron volt, or 1 voltage, giving it 1 volt, giving it 1 electron volts worth of energy. The proton having, let's refresh everything that I brought up here. It's just the stuff, right? Nothing new, all old. Okay. I mean, there's lots of other things I could have asked, of course. What was the acceleration of the electron? How much force the electron experienced? I mean, all this kind of stuff. It's all little minutia stuff. But you should have it. Right? Nothing new. New stuff now. Okay? Just done. If I tell you that I have a charge Q here, and I'm going to put another charge here that is a proton. Okay? And at that point, the proton has 1 eV of energy. How much charge must I have here? I'm trying to see if you can bring some of these things together that we just did with the uniform field to this problem. I will remind you, the electric potential from a point charge is Q over 4 pi epsilon naught r. And I'm saying this proton has 1 eV of energy. Now, what I'm telling you is that you're a volt away from the central charge. That's what I'm telling you. Because if a proton has 1 eV, then it must be 1 volt. Work it out tonight. It's not that tough. So let's walk through it. Right? This is an expression for the electric potential everywhere around a point charge. You'll notice that the electric potential gets smaller the further away from the point charge you are, right? And it gets bigger the closer you get. That's what this R is right here. As R becomes a smaller number, the electric potential becomes a bigger number. Fair enough? Everything else is more or less a constant, except this time we don't know how much charge there is. And in fact, that's what the question was. If I'm bringing a proton up, and the proton's going to be right at this location. Really? Really? 2 noises? So we say that we want the proton to have 1 eV of energy when it is located a centimeter away. So let's remind ourselves an EV of energy is just, the charge on the proton, which is the same as the charge on the electron, times the voltage, which in this case is 1 volt. So 1 EV, 1 electron volt. So that means we are at that location. Oh my word, I'm going to freak out. At that location, you get rid of the proton. You don't have to worry about the proton for this. This point is 1 volt. This location in space has an electric potential of 1 volt. If the proton when there is 1 EV. Is that okay? You follow why I'm saying that? Okay, because if so, that just means you set this equal to 1. And solve for Q. That was all I was asking you to do yesterday. I'm going to do something harder today. But that was all I was asking you to do yesterday. And I modeled it, done the same thing. We're just working the problem from a different type of field. Right? The other one, the field was uniform. This one, the field's not uniform. So if I want to know how much charge has to be here, it's pretty straightforward. Q over 4 pi epsilon naught. In this case, R is 0.01, right? 1 centimeter has to equal 1. We're finding how much charge it would take to make 1 volt of electric potential a centimeter away from a central charge. So as a problem goes, there's not really much here now. Put in your value for epsilon naught, put in your distance. And this will tell you how much charge is, and this will be in coulombs. But that's all I was asking yesterday. What a volt really is. Okay. So a lot of what you said doesn't really work out. So let me you're trying to draw a parallel between gravity and electricity. And your first parallel is to say, well, for gravity, you could change something's potential energy by changing its height relative to the Earth. This only works if we have a uniform gravitational field. But if you want the analogy in a uniform electric field, it would be QE delta D or something like that, where that represents the perpendicular change in your displacement inside the field. Okay, so here, ground, and we lift something up. Here, say, 2 plates, and we move a charge from here to here. Okay? Now, what you are trying to conflate, the mg here would be QE here. So your intrinsic property that is acted on by that force and the size of the field, which in this case just ends up being the acceleration of gravity, same idea on the other side. Okay? The problem with that is that only works in a uniform field. But all the things we talked about when it came to potential energy still work. Now, the thing that you're trying to do is you're trying to understand what a volt is. And in these two contexts, what I was trying, and my picture's not going to work for this, so let me try and do a better job here with my picture. What I was trying to convey to you is that between here, here, and here, H0, H1, H2, I don't have to tell you what you're lifting for you to recognize that the object will have more energy at H2 compared to H0 than H1 compared to H0, right? That's kind of like the electric potential. That I know there'll be more energy for a given object as it gets further away from the surface of the Earth, to a degree, as long as we're in a region of the space where the gravitational field is uniform. A similar condition is to have, say, a region of space where there are two charged plates, say one minus and one positive. This generates a field, but the electric field in this case goes from the positive and towards the negative. So if we set this as D0, then if we set this as D0 and say this is D1 and right here is D2, a proton will have more energy at D2 compared to D0 than at D1 compared to D0. Because technically, I would have had to do more work to take a positive particle and move it all the way to D2 than it would be to move that particle all the way to D1. But I don't need the particle for that conversation. I can just say, for a given charge, there will be more energy at D2 than D1. So that's speaking to the electric potential, because electric potential is the energy per unit charge. We don't talk about it for gravity, but we did spend the whole first 3 weeks on kinematics questions where we never needed the mass of the object. Its speed was just related to how far it fell. That was because, in general, the mass didn't matter. But if you're, say, trying to drive, a stake into the ground, well, I can choose a small hammer for that or a big hammer for that. Which of these will do more work? The big hammer will do more work because it has more gravitational potential energy. It's a bigger object. It takes more work to lift it. So it has more energy, even though they're both at the same height. When we're comparing these two objects at the same height, the mass would matter when it comes to how much energy there is. And the same for if I have two protons or one proton. Well, one of these has more energy when moved to here, right? Because there's more charge there. But it doesn't change that the space over here would give a charge more energy than the space over here, right? That's what we're trying to compare when we talk about electric potential. So I'm telling you that there's something special about the space here that's different than the space here, right? Charges placed at D1 have less energy than those same charges placed at D2. Again, the gravity analogy works the same for this. Now, we do have some complications because we also have negative charges, right? So the reverse is true for the negative charge. It will have more energy at D0 than at D1 relative to D2 because it's going to go in the opposite direction. That okay so far? All right, so then this analogy keeps going if you want, but it gets more difficult to consider because when you stop dealing with a uniform gravitational field, again, some people in this room never had this, but if you don't have a uniform gravitational field, your energy, your absolute amount of energy, now it depends on how, oops, not R squared. Now it depends on how far away you are from the planet. It's negative though, because there's only one type of material. Mass isn't positive or negative, so it's an attractive force only. So the work to get away releases you from being bound to the Earth. Well, we have this exact same thing happening for electric energy too, in that the electric potential around a point charge is Q over 4 pi epsilon naught R, which means the potential energy is going to be Q1 Q over 4 pi epsilon naught R. Okay? Now here's where it gets a little bit weird. So let's say I have a large positive charge in space here, just like if I had a large gravitational well here. If I bring something, we don't have to bring it there, but if we have an object that's here that has mass m, it has less energy than here because the energy is negative. So the number's bigger, but it's a more negative number because it's closer, right? It takes energy to get away. I'd have the same thing on this side if I have a negative charge here, right? That will make this equation negative because one of the charges is negative now, and it would take energy to separate them because it's an attractive force. So I would have to give energy, I would have to put energy into the system to pull the electron away in the same way as I'd have to put energy into our object to get it away from the Earth. But we have the reverse of that if it's a positive particle. It's actually harder to get these two things closer together. And because of that, they have more energy. It takes energy from you to get them closer together. Does that make sense? So, but getting away from the energy discussion, we know that it will take more energy to get to place 1 than to place 2 if it's a positive particle. Right? But it'll take more energy to get to place 2 than place 1 if it's a negative particle. Right? It's about the location. That's the potential part. The potential is about the location. But the energy becomes about the interaction of two things. Right? I have to have a charge to put there. There'll be more energy at these places if I put more charge there. Right? But the potential is about the place, just like the field is about the place. I know I'm talking to Gokul, but I really think I'm hoping I'm talking to the whole class. So I was answering his question. So sorry I kept looking that way. But I'll look this way now. He's gotten enough of my attention. I'm all better now. Sorry. I'm somewhat left-handed. Do you know what that means? You look to the left. You do. You're left-handed. Right-handed people look to the right. Can't really help it so much. It's just the way it goes. So, based on what we just talked about, I want you to consider this situation for just a minute. Just need something to hold the form of a square for a second. Let's say you wanted to arrange 4 charges in space. Let's say that they're all the same size charge and let's say that they are going to be placed in a square, so they are all, on the vertexes of the square. How much energy is there in this system? Let's go even one step further. Let's say that all the Qs are 2 microcoulombs of charge, and let's say we're placing them, I don't know, we'll go with 5 centimeters apart. So we're going to try and figure out how much energy there is creating this. Okay. Now, to figure this out, it's not a particularly hard question, because you can probably realize that to bring these things together, you have to work against their natural repulsive force, right? They're trying to push each other apart. But we do know stuff about the system. We know that between any 2 particles, the potential energy's got to be Q1, Q2 over 4 pi epsilon naught times R. Right? That has to be the energy between any 2 of them. Follow so far? So let's talk about how you would figure out the total energy here. Now, if it were me and you're trying to do this, you can't do this the same way I'm going to. So I would draw multiple pictures if I were you. Because what I'm going to do is I'm going to take away all that was here except for the square. And I'm going to describe the process of assembling this system. So the first thing you have to understand about this process is that the first object that you place here doesn't cost you anything. There was nothing in the space before, so there was nothing for this particle to interact with. So it required no energy to place the first particle, right? Nothing to interact with. However, the moment you want to go place the second particle, then you have to deal with the fact that there was already a particle there. So bringing in the second particle requires consideration of the first. These 2 must have an energy associated with them being together of Q times Q over 4 pi epsilon naught times R, which in this case is the side length S. That makes sense? So that's the amount of energy associated with just those 2 particles. And we can work that out in joules. We have values. So if you wanted to work it out in joules, you could do so. But we're not done yet, right? We have more assembly to do. So let's consider that we're going to bring in another particle. Now remember, this is path independent, so it doesn't matter where this particle comes from or the path it takes to get there. All I have to do is say that I'm taking another particle and bringing it someplace into this square. Again, path independent. Now, this particle has to interact with 2 other particles that are there. So obviously, one of the potential energies is going to be Q times Q over 4 pi epsilon naught S. That's these 2, right? However, these 2 are also interacting. So plus Q times Q over 4 pi epsilon naught. And am I okay just to write root of 2 times S because we know that it's the root of 2 across a diagonal? That's all good? All right. Well, that brings us to our last particle. But it interacts with the other 3 that were already there. But I can kind of go pretty quickly here, can't I? Aren't there going to be 2 of these? Because there's this interaction and this interaction. And there's going to be 1 of these. Well, we've already worked out the math for those, so I don't have to really work it out again. So I think we can pretty much jump right to 2 times Q over 4 pi epsilon naught S plus Q times Q over 4 pi epsilon naught square root of 2S. Together, that's the total energy of this system. So I could add all of that up, and I'm noticing I have 2, 3, 4 of those. Do you notice that? So 4 q squared over 4 pi epsilon naught s, plus I have 1, 2 of these. So q squared over 4 root of 2 pi epsilon naught s. Right, this would be the total energy of the system. Now, if you were trying to work this out, make your maths, work for you, I would pull the q squared over 4 pi epsilon naught s out front of this, which will leave you with 4 plus, I made a mistake. There's a 2 here. So, yeah. 4 plus 2 over 4, 2 over root of 2 there. Think I did that okay? Yeah. Pulled out the q squared 4 pi epsilon naught s, that leaves a root of 2 in the denominator, right? Okay. Now, this is just a value in joules, by the way, right? You put in your charge, put in your distance, and this will give you something in joules, which we could work out. We could get an answer in joules. But I want to go one step further with this. Did you guys follow this to this point? There's no direction. There's no complicated vector stuff. Potentials add together. If they're in the same region of space, they just add together. So one of the things you could have done, and we were kind of doing that, is we could say, leave that particle out and figure out what the electric potential is at this location in space. Right? We have 3 other contributions to the electric potential there. And those 3 contributions would tell us what the total electric potential is there. So then we can put any charge there that we want, and we know how much energy would be there. That's one thing we can do. There's something else we can do, though. I'm going to get rid of some of the stuff that's on the screen that's distracting. What if you were to suddenly release this system? What would happen? There's a certain uniformity of the system, don't you think? So I would probably likely get all of these spirited away in opposite directions, right? You could estimate how fast they'll be going after they separate, because you have the total amount of energy. So that's just got to be equal to 4 times the kinetic energy of the individual particles. Right? That would have to be. Let's try this. I want to try this in a real situation. I brought this up earlier, but now's the right time to figure it out. In the sun, fusion at the core is fusing hydrogen and helium. That's for a young star. Now, as stars mature and age, they start fusing other things at their core. And you kind of think of it like it's not really like this, but like a layered gobstopper with the heavier elements sinking to the center, and they're fusing to make even heavier elements. It'll probably a little more chaotic than that, but it's kind of the vision I have in my head. But when a star begins, it starts by fusing hydrogen into helium. The problem is that the type of hydrogen that exists in the universe is almost all just protons, so hydrogen 1. So hydrogens won't form heliums. There's no helium 2. Right? You talk about the way helium isotopes are. You can't get 2 protons close enough to bind each other. But you can get 2 deuteriums to do so. So what we believe happens in the sun is what's called the proton-proton cycle, where H1s form H2 and eject a positron. So what's happening here is the formation of deuterium. This process doesn't require the same kind of energy that you might think, because the neutron is neutral, so there's no Coulomb repulsion there. They just hit each other And through, I guess, what we'd call the weak nuclear interaction, one of the quarks is changed, and we suddenly go from a proton to a neutron. So that process we're not going to talk about much today because I don't know how much energy is actually released in that process. But the process we are going to talk about is the second process, where two H2s form a single helium. This process we can talk about. What's kind of amazing about this is that the hydrogens are, of course, positively charged because it's going to be an ion. When you're in a hot plasma like that, there's no electrons around. So these are just two positively charged particles. And because they're protons, it's 1.6 times 10 to the 19th coulombs of charge. Now, in order for that to actually happen, the two deuterium atoms have to get close enough together to have the strong nuclear force pull them the rest of the way and bind them in a nucleus, which means they have to get past what's called, there's a Coulomb repulsion barrier. That's about 2.5 times 10 to the negative 15th meters, 2.5 femtometers. Now, this spacing is pretty much true for most atoms. So even like a uranium atom has to exist inside a range of about 2.5 femtometers. The outside edges of it generally are on the outside of that, and they are pushing it apart, which is why your bigger atoms will spontaneously fission, because the outside edges of them are outside the Coulomb repulsion barrier. The parts that are pulled in are the parts that are inside the 2.5 femtometers. And so that's why a lot of atoms are very stable, because most of the mass is inside that, but the bigger ones not so much. So here's the question I want you to know. First, how much energy is there, potential energy, when you get these two deuterium atoms within 2.5 femtometers? We should be able to calculate that with what we've just done. So let's start with that. How much potential energy would there be to get these two particles 2.5 times 10 to the negative 15th meters apart? We just did this exact same problem with 4. I think we can do it with 2 charges. Right? Doesn't cost anything for the first one. It's all about the fact that we get the second one in there. So there you go. You have all the information you need to calculate how much energy there must be right when we pass the Coulomb barrier. So take a minute, grab your calculators. If you need a reminder, elementary charge, 1.6 times 10 to the negative 19th coulombs. The permittivity constant, 8.85 times 10 to the negative 12th meter squared per Coulomb squared Newton. There we go. The amount of potential energy they had came from kinetic energy originally. Well, this one, there's no reason for you to know this, but I think some learned people should know it. Kinetic energy equals 3/2 the Boltzmann constant times T when this is in Kelvin. You would have learned this in chemistry, but you didn't. So I want you to know about it now. So if you have a hot plasma, a gas, and you want to know how much energy the gas has, you just need to know its temperature. Well, I want to do the reverse. How hot is the center of the sun? This has to be the temperature of the center of the sun for natural fusion to take place. So let's work this backwards. You'll need the Boltzmann constant. The Boltzmann constant is 1.38 times 10 to the negative 23 joules per Kelvin. So this answer is going to give you the temperature of the inside of the sun in Kelvin. when you get that number, that's not the hottest part of the sun, by the way. But it's got to be very hot in order for this nuclear fusion to not just occur, but to continuously occur. So remember, when this is occurring in the star, it's releasing energy. What form does the energy take that it must be releasing? Do you have any idea? Because I think this is where all of your sciences have probably failed you to a certain degree. So